Modern vehicles are essentially supercomputers on wheels, processing millions of data points every second. To handle the inevitable wear and tear of computer hardware, the auto industry relies on strict functional safety standards, specifically ISO26262. In traditional legacy systems, safety relied on a fail-safe approach. If a computer fault was detected in the power steering or brakes, the system immediately shut itself down and forced the human driver to take manual control. Today's autonomous systems and advanced driver assistance features operate at highway speeds without an active driver ready to take the wheel. Simply shutting the system off in the middle of a lane is a fatal flaw. They require a fail operational approach, meaning the car must keep steering and braking even when an internal error occurs. To guarantee that continuous operation, engineers mandate strict diagnostic coverage.
But safety mechanisms are built into the architecture to detect the most microscopic anomalies, from a tiny voltage drop to a nanosecond of clock delay. The definition of automotive safety has evolved. Success now means guaranteeing the system never makes a catastrophic miscalculation while in motion, ensuring the computer remains as reliable as the mechanical components it replaced. But making a computer hypersensitive to microscopic faults introduces a vulnerability, the false positive. Hardware is constantly exposed to environmental noise. A high-energy subatomic particle, like a cosmic ray, can extract a microchip and temporarily flip a single bit of memory, tricking the hypersensitive system into a panic state. If the safety mechanism interprets that temporary glitch as a critical failure, it triggers an unnecessary system shutdown. The car itself is perfectly fine, but its usability, or its availability to the driver, drops to zero.
The alternative creates a second problem. Continuously running deep diagnostic tests consumes massive amounts of processing power. If the processor is busy checking its own health, it is starved of the resources needed to actually calculate steering angles or braking pressure. This is the core engineering paradox. Blindly pursuing total hardware safety through constant heavy testing results in a vehicle that is technically fault-free, but functionally paralyzed. To understand why standard software testing fails here, we have to look at the physical time constraints. Engineers operate within the fault-tolerant time interval, or FTTI. This is the window, often just 10 to 50 milliseconds, between the moment an error occurs and the moment it causes a crash. The standard defense is a software-based self-test, or SBST. This is a library of code designed to check every component inside the processor for permanent hardware damage. Look at this timeline representing that 50 millisecond FTTI window. If you run that massive SBST sequence as a single uninterrupted block, it overruns the time limit and squashes the driving algorithms out of the schedule. You cannot pause a vehicle moving at 70 miles per hour to run a comprehensive system scan. Standard software testing directly conflicts with real-time physics. The solution is time slicing. Instead of running the test library all at once, engineers break it into fragments called microruns. These slices execute in an interleaved loop. The processor runs a microtest, pauses the diagnostic, steers, and runs the next slice. This repeats thousands of times per second. This rapid toggling relies on a process called context saving. Before every jump between tasks, the CPU must memorize its exact state and data down to the bit. Otherwise, the transition will corrupt the entire system. Time-sliced execution resolves the CPU starvation issue. It allows the processor to maintain real-time vehicle control while continuously sweeping the background for permanent hardware damage. With the background scanning optimized, the system still needs to handle those transient faults, like the cosmic ray strike, without shutting down for every temporary glitch. The first line of defense sits in the hardware. Error correction code, or ECC, silently catches and repairs single-bit memory errors without ever interrupting the main CPU. For errors that make it past the memory, the system uses a software debounce filter. Instead of reacting to the very first anomaly, it acts as an error counter, watching the frequency of recurring faults. The system requires the error count to cross a predefined threshold. Only then does it declare a permanent, dangerous fault and trigger a safe state. This layered filtering ensures the vehicle ignores harmless environmental noise, preserving maximum availability to the driver without compromising the detection of genuine hardware failure. In highly complex software-defined vehicles, processing power is becoming even more scarce. Even the micro-sliced software tests can consume valuable bandwidth. Designers are now physically hardwiring the diagnostic testing logic directly into the silicon chip itself, a method called hardware built-in self-test, or BIST.
The vehicle's real-time operating system acts as an orchestrator, triggering these hardwired tests in the background without stealing any computing cycles from the main CPU. Embedding the tests directly into the hardware allows for maximum diagnostic coverage with virtually zero penalty to the system's performance. A verified microchip is the mandatory foundation for autonomous AI dealing with real-world confusion. Engineers refer to this as safety of the intended functionality, or SOTIF. High-level fusion controllers use these real-time hardware health reports to rule out internal failures. If a sensor is confused by a complex shadow on the road, the system can verify that its own internal logic is healthy, allowing it to focus on reprocessing the sensor data rather than triggering an emergency shutdown for a suspected hardware fault. Modern safety relies on this continuous loop of internal verification. By proving its own hardware is sane every few milliseconds, the vehicle maintains the trust required to keep moving forward through a complex world.